Hello and welcome to another workshop. This is workshop number 3 for the Widener ME474 Introduction to Finite Element Analysis course. Tonight we are going to be taking a look at this workshop, which is basically a simple 4-point bend type of a problem using an aluminum bar with rigid bodies. So for our class, this will be the first time that we are using a few of these features. Number one, we will be dealing with rigid bodies, which we have not dealt with yet. We'll also be dealing with the interactions module, as to this point we've only really done problems with one part, and tonight's problem will be an assembly with multiple parts, so we will be using some of the features within the interactions module. So I'll make sure to highlight those items as we move through. If you open up your Abaqus CAE Student Edition, we are using the 2017 version. We're going to start out on the part module. So the first thing that we're going to do, if we go back to our part here, it is the problem statement says it's 20 millimeters thick and 250 millimeters long. So we are going to be able to take advantage of half symmetry here at least, where we can split the problem right down the middle, and we're going to model just the left half. So if we do that, we're going to make our problem 125 millimeters long and 20 millimeters thick. So we're going to go ahead and draw that part first. So we'll do create part, and we will call this the bar. It is a 2D planar deformable part. Shell, and for an overall size we could just type in 500 here to make sure that we don't go off of the grid. So we'll say continue, and I'm going to use the rectangle tool, and you'll see down in the bottom here Abaqus wants you to pick a starting point for the rectangle, so we'll start at 0, 0. And we're going to only be drawing that left side, so I want to go in the x direction. We're going to go negative 125. And in the y direction we will go up 20 to get our overall bar thickness. That's the only thing we have to draw for this particular part, so I'm going to say that I'm done, and that I'm done with the sketch. And there is my initial part, the bar. Next up, we're going to draw the second part, which is the roller. So just to remind ourselves again, the rollers have a diameter of 20 millimeters. So we're going to go ahead and create a rigid body here that is a roller with a diameter of 20 millimeters. So we'll do create part. Let's call this one roller. It is a 2D planar. This one is a discrete rigid and wire, and we can leave the size where it is. So we'll say continue. And when I come in here now, we're going to take advantage of the create circle tool. And again, down at the bottom, Abaqus prompts me to pick a center point for the circle, so I'm going to say 0, 0. And the problem statement said that the diameter is 20 millimeters, so if I'm really just defining a radius here, so I'm going to say that I'm going to 10, 0. And actually, to make this, 10, 0 is fine. Okay, so there is my circle. I am done drawing circles, and I'm done with the sketch. So there is my rigid body that I have now created. So those are the only two different parts that I'm going to need in this particular module. So I'm going to move on now to the properties. Actually, we'll go back to the parts for a minute. So what's unique about a rigid body is that later on we're going to need a reference point for this part as well. So we have to define the reference point. If I come up here to Tools on my drop downs, you'll see that there's a button here for reference point, and Abaqus says select a point to act as the reference point, so we're just going to choose the center of the circle. I'm going to say OK, and now you'll see this reference point shows up. With a rigid body, all of the surface or the nodes or whatever it is that you've created, you're going to tie them back to just one central point. And I can impose my boundary conditions and initial conditions on just that one point, and we don't have to actually do anything to the rest of the body. So we'll talk about that again in a minute, but we do need to create that reference point. So now if I move down to properties, we're going to create our material. So we were told that it is aluminum. And under mechanical, elastic, and elastic, this is just the simplest material property really that we can use. So if we are in millimeters, we're going to be defining the modulus in terms of megapascals. So we'll do 70,000 for 70 gigapascals. And a Poisson's ratio, we'll choose 0.22. Okay. Next up, we need to create a section. So the second button down is my create section. For this one, we'll call it bar. I realize that the roller is still what's displayed in the screen. We're not actually going to have to create a section for that. So we'll have to make sure we switch that over before we assign the section. But for creating the section, it's a solid, it's homogeneous, it's a bar, and we're going to use our aluminum material that we just created. So now in this drop down here next to part that right now says roller, I'm going to change that to bar so that my bar is displayed on the screen. And I will do assign section. And Abaqus at the bottom says select the region to be assigned a section. So I'm going to choose the whole bar. And I'll say done. And then I'll see that my bar shows up here. So now I can say OK. And we'll notice that the part has changed colors, indicating that I have indeed assigned a section to that part. That's going to do it for the property module. So next I can move down to assembly. And this will be a little bit different for the course so far as well, as we have not actually had to build an assembly with multiple parts that we need to align. So the first thing we'll do is we'll bring in our bar. So I'm going to create an instance of the part bar, and I'll say OK. And next up, we're going to bring in an instance of the roller. So I will select the roller, and I will say OK. Now we know that the bar has a thickness of 20. So what I want to be able to do, and we also know that the diameter of this roller is 20. So I need to move this circle up so that way the bottom edge is just touching the top surface. And then we're also going to have to move it over. So let's take a look at how far we're moving it over. If we go back to the problem statement, we see the very last line says the span on the bottom is 200 millimeters. So center to center here is 200. And on the top, center to center is 100 millimeters. So when I go and move this piece up, I'm also going to need to shift it over 50 millimeters from that symmetry edge that we're using here for the top. So what that means is that if I want this piece down here at the bottom to be flush with the top, I know I'm going to have to move it 20 units plus 10 units, so I should be moving it up 30 units to get that to be touching the very top face. And then I'm also going to move it 50 units over to the left. So if I use my translate instance button and I select this roller and I say done, what Abaqus asks me is to select a starting point for the translation vector. So if I start from 0, 0, I now know in the x direction I want to move 50 units in the negative x, and that I need to move 30 units in the positive y direction. So when I do that, I'll see now that my roller appears to be just touching the very top and moved in 50 units from the middle of the part. Okay, so that looks okay to me, so I'm going to say done. Now we're going to have to bring in another instance here of the roller for the bottom. So I will say okay. For this one, again, we need to move it down so that now it's touching the bottom, which in this case we are lined up with the bottom face at the center, so I need to move it down 10 units. And then our problem statement said that that overall span on the bottom is 200, so I need to move 100 units over to the left. So if I use my translate instance again, I will select that roller. I'm going to still choose 0, 0 for the start, and I'm going to move us now 100 units in the negative direction, and we need to move 10 units in the negative y direction, and that should line us up nicely with that bottom face again. So I'm going to say OK, and it looks like we've lined up our rollers where we wanted them to be lined up. So for my assembly, we are now complete. So we'll move down to step. For this one, it's going to be the same as what we've been doing so far in this course, so we're going to create a step. Maybe I will call it bend. it's going to be a static general step, so we don't need to change anything here. But maybe just like the last problem we did, if we wanted to see some intermediate steps here, we will create the initial increment size to be 0.1 with a maximum of 0.1. So what that means is, if we go back to the basic tab, my overall time period is 1. So using these increments now, I can say that the most it's ever going to move, the most it's ever going to move is a 1/10, and initially it's going to start at a 1/10. So assuming that we don't run into any issues at all, it should complete this model in 10 even increments, and I'll be able to create a small video or animate this or just step through the contour in smaller bits, so that way we can kind of see how the stress or how the deflection or whatever it is that we're interested in looking, how that developed throughout the problem. So I'll say OK. Now if we change to the interactions, this one's going to be a different one than what we've used before. It's a little bit easier now than it used to be for contact, as over the last few years Abaqus has implemented the same general contact that used to only exist in the explicit dynamic models. Now that is a feature that is offered as well in our static models, so we'll be taking use of that feature. We also have to, in this step, tell Abaqus about our rigid body, so we're going to start off with that one first. So under Create Constraint, which is the third button down, you'll see that there is a type called rigid body. So for a name, let's call this one top roll, because we're going to use it. We have to do it for both of them. We'll say continue, and that brings up this prompt where we have a few different options that we can look at here. For us, we're gonna choose, or we're gonna show Abaqus which body it is that we're using. And I use this little cursor arrow next door here, so I'm going to click on that, and I highlight the circle on the top. I'll say done. And then it also needs me to highlight what the reference point is for that particular rigid body, so I'm going to choose that reference point. And when I say OK, we will now see these little circles showing up. So I've indicated to Abaqus that this is in fact a rigid body. So I'm going to do the same thing with the bottom one here. It's Create Constraint, rigid body. We can call it bottom roll. And I have to highlight body here and use the arrow to say it's this. Done. And for the reference point, it would be that reference point. And I will say OK, and we'll see here now that I have created another rigid body. The next step that we need is to create our contact. So that is under Interactions. Anytime we've got two parts that are interacting with each other, it's going to be under Interactions. So we will call this one Contact. And by default, Abaqus moves to the step that we created. But if I roll this back to the initial step, we'll see I've got some additional options, including General Contact. And so that's what we're going to use. What that does, and you'll see this a little bit on the next screen, is that it's going to automatically define contact with all parts with themselves. So what that means is that in the very beginning of the problem, all the different parts that we have in our assembly are going to introduce themselves to each other, and they're going to say that all of us are allowed to contact you and ourselves. Before, we used to have to define each individual contact pair. Like I said earlier, in explicit, in the dynamic models, you had this feature here of general contact. So that's a slightly newer feature in Abaqus to be able to do that on a static model, and it does make your life a little bit easier, assuming, of course, that you would like the same contact constraints implied on all of your parts. If that's not the case, then you may have to go back and do some of these, pair by pair. So one thing we do have to define, though, is the global properties. So we haven't done that step yet, but you'll see the little button next door here that says Create Interaction Properties, so we can do that right now. We'll call this one Contact, and for the type, it is a contact. So if I say Continue, you'll see this prompt come up where Abaqus gives us a chance, kind of like when we create material properties, I can now create a variety of different contact properties as well. So if I click on the drop down for mechanical, really the two that we are typically most interested in would be tangential behavior. So when these things are going to slide across each other, what's going to happen? In our case, we can probably just use frictionless in a 4-point bend. Generally that's what you're going for. Perhaps there are times where maybe you would like to input your specific frictions, in which case you have a variety of different options here that you can use. But in addition to that, we will also have to define the normal behavior. And again, there are other options here where you can allow for Abaqus to have some type of a cushioning there. So if this is intended to be a softer material, or you're going to allow something to penetrate through before a contact is really imposed, you can do that here as well. Also, this button for allowing separation after contact, what that does for you is if we turn that off, what that would be telling Abaqus is that once they come in contact, they can't separate. So if you were the example I always think about is like throwing clay at a wall or something that it's going to hit, it's going to stick to the wall, and then it's going to be stuck there. In our problem, we're going to allow contact after, allow separation rather after contact. But there might be times where, if you're gluing something together and you want to simulate that in Abaqus, then you could in fact have it not allow that separation after you've contacted. So those are the 2 steps you need to make sure you get. It's a very common error to either only get one of those or something. So it's very important that you have both of those features at least. And so we'll say OK. And now I need to choose that from my drop down here so that it says contact in my global property assignment. And I'm going to say OK. And I can see down at the bottom that the interaction contact has been created. So it doesn't really highlight anything on the screen. But we can at least see that I have created that property. Okay, so for interactions, we're all done. Next, we can move into the loads. So we've got a few different loads that we need to impose here. One would be a symmetry face over on the far right in the X direction. That is the one that is perpendicular to that face. We also need to tell Abaqus that this bottom roller is going to be fixed and that we're going to move the top roller. Did we give a... we just said a few millimeters, so we're kind of just picking a number here and we're going to deflect that top roller down a few millimeters. So maybe for us we'll choose 5 millimeters. Okay, so let's start off with the symmetry boundary condition. If I do create boundary condition, I can choose symmetry, and we'll give this one a name of SymX. I'll say continue. I'm going to select this edge, and it is a X symmetry boundary condition. So when I choose that, I'll see that in fact it has highlighted a few points along that face, showing me that I have created a boundary condition there. If I next do create boundary condition again, and we'll do this one for the bottom, and in this case I want that roller to be fixed. So if I say continue and I choose that reference point, I can use our encast feature to just lock that that roller so that it can't move at all. And again, I'll see that variety of different little arrows show up there, showing me that I have created a boundary condition on that point. The last one I need to do is for the top roller. So if I do create boundary condition, and we'll call it top. If I want to move it, I do need to move this away from the initial step to the bend step, because otherwise in the initial one, we're not allowed to actually impose any movement. We're only allowed to fix things. So in the next step, the first one that it's actually a static step, I can tell Abaqus that I want to fix it in some directions, but I can actually type in a value for how far I want that to move in this particular step. So it's going to be a displacement. I'll say continue, and Abaqus is going to ask me select where I want to impose that, so it's going to be on this reference point. And now it brings up this window that we've seen before, so I'm going to say it can't move in the 1 direction, in the X direction. In the 2 direction, I want it to move 5 units down, because I can see my compass there in the top right is showing positive Y to be up, so I want to move this roller down. And the rotation about the Z-axis, I want to fix that. I'm not going to let my roller just move around. It is important that you get all 3 of those boxes checked. It's a very common mistake to only type in the one value and not select the other ones to 0. And what that does, especially since we defined our contact to be frictionless, is that Abaqus will think that that top roller is allowed to move off into infinity because you haven't constrained it. and you'll start to get messages about an unstable problem that you're trying to solve. So it's a very common error. If you do start to see errors when you're running, this is always a common thing to go back and check and make sure that you defined. So when I say OK, I can see that I've got my arrow pointing straight down, and it appears that I've created the correct boundary condition. So if I move now to my next step of meshing, we do in fact have to create a mesh for both parts. If I select part, we can start off with bar, and the first thing I need to do is to seed the part. So let's say, well, let's see what the default one looks like. It's pretty coarse, so maybe we'll drop this down to something like 6. Let's see what that looks like. And that's pretty good. We'll have to make sure we don't have too many nodes and elements here for the student edition, but if I say OK, and we can check what types of elements we are using. So I'll select that part and say done. And right now, by default, Abaqus has suggested plane stress, linear. It's kind of your very fundamental, just 4-node brick for a 2D problem. So I'll say OK. And then I want to use the second button down for a mesh part. And it says, is it OK to mesh the part? And here's the mesh that I have created. We'll see if this is fine enough. It created only 63 elements, so I actually probably could create a few more if we needed to, but we'll see how this problem looks when we go to solve it. I do also need to put a mesh on the roller. So if I come in here and I will seed the part, and it has given me an approximate size of 2.8, so let's see what that looks like. That looks pretty good. If I say OK, I can check the element type here on this one as well, but there's really only one type that we can choose from, a discrete rigid element. So that's fine, and I will mesh the part, and in this case it's a little bit harder to see, but we can actually see, especially in a circle, it will kind of show us how it's now slightly pixelated because of that meshing, but it should be sufficient for this problem. So that's it for the mesh. If I move on down to job, I can now I have to create a job for this model, so let's just call it workshop 3. See if I've already used that one before or not. I say continue. Again, we're not doing any parallelization here, so there's really nothing that we need to change in this screen. And I will now tell Abaqus to submit. And once it's done thinking, we can go to monitor. And we can just watch and see what comes up here. So it started through Abaqus. Solving a standard, we can see that it took its 10 little increments, and now it appears to have finished. So if I dismiss, I can look at our results, and if I look at the deformed shape, it's actually not too bad. We probably don't really need any more elements. I think we do have some to spare if we wanted, but it doesn't look like we've got too much zigzagging and buckling going on. So this does appear to at least be a sufficient number of elements for our particular problem. We can also see the contact was imposed correctly. We didn't have any rollers passing through the bar. That's a common problem that you might see if you didn't define contact correctly. Your pieces that are moving will just pass right through each other instead of actually deforming anything. But in this problem, it appears that we've done that correctly. You'll also see that there is a scale factor here at the bottom. So if it looks like that moved a lot more than just 5 millimeters on the screen, it certainly did, because we have enlarged that somewhat. So now at this point, I think it was just asking us to, kind of poke around and see what sorts of values we have, so we can look at contour plots. And again, maybe we could say that, yeah, we probably could use some refinement in here, since we've got a very coarse mesh, or coarse contour of going from one max to the other max, and then back to the other max again, all within just 3 elements. So, in an ideal world, we would probably control that a little bit better. But again, for our purposes, we can at least get the idea of how to do it. And then if we were using the industrial version of the software, you could apply as much mesh to that region as you would like. We can also look at the deflection contour if you'd like. We can see, this is just the overall magnitude. But if we look at the specific directions, so what moved in the X direction, what moved in the Y direction, we get a feel for how this problem is deforming. We can also go ahead and animate this if we wanted to. So if we do, let's try to change some of the settings here. We'll slow down the pace because I know that it always wants to do that fairly fast. Let's say OK. And so we can actually animate this if we want to. This is animating based on deflection. But you could animate on any of those different parameters that we would like to. If we also want to create the mirror here, we can go to View, at the top, View, ODB Display Options, and we can go to Mirror. And in this case, we would like to mirror this about the YZ, I believe. And if I say OK, and then we can zoom this out, I can see that Abaqus will mirror that over the YZ plane, and I can now solve a problem that looks very much like what it did on the sheet. So we didn't actually have to do both sides, but we can trick the user interface into displaying both sides. So that pretty much concludes the workshop that I had lined up for you for this evening. As always, if you have any questions, feel free to reach out. But what we learned in this particular section tonight is the idea of a basic introduction to contact, and also using an assembly where we needed to move and align some parts. And we also touched on rigid bodies for the first time, so a couple of new features that we haven't talked about before. So hopefully you will find those useful in any of your projects moving forward. And like I already said, if you have any questions, feel free to reach out. Otherwise, I look forward to working with you on workshop number 4. Thank you very much.